Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So today our group, which is Group 1D, will present to you about our initiatives and projects for Hakimi Productions. So first of all, let me introduce our group members first. So my name is Ariff. We have Sabrina, Batrisyia, we have Lim Ming Yang, and also Mohd, then Asyraf.
Okay, good day everyone. Now I will be presenting our project on the production of cumin itself, also known as isopropyl benzene. So what is cumin? Cumin is an important intermediate chemical used in the petrochemical industry. It is mainly used to produce phenol and acetone, which are essential raw materials for any industrial products. These chemicals are widely used in the manufacturing of plastics and synthetic fibers, resin and adhesive, pharmaceuticals and medicine, and as well as coatings and paints. Due to increasing global demand of this product, designing an efficient and sustainable cumin production process has become highly relevant in modern chemical engineering. In overall, the plant is designed to convert benzene and propylene into cumin through an alkylation reaction, commonly known as the UOP cumin process. So we're moving on to the process structure. The cumin production process can be divided into several main sections. The first section is feed preparation. In this stage, the raw materials, which are benzene and propylene, are stored, pumped, and also preheated before entering the reactor. The second section is the reaction section. Here, the main chemical reaction takes place inside the reactor where benzene reacts with propylene to produce cumin. The third section is the separation section. Distillation columns are used to separate the desired product from unreacted reactants and byproducts. The fourth section is recycle section, where unreacted benzene and intermediate byproducts are recovered and returned to the reactor to improve process efficiency. So finally, the last section is the product storage, where the purified cumin product is stored before being sent to downstream industries and for further processing.
I'm going to introduce about chemical engineering fluid mechanics in this process. So the objective is to transport products efficiently, continuously, and safely throughout the unit operation. We will prepare a practical piping line layout where suitable pipe materials, diameters, and fittings are selected. So by choosing a practical piping line layout, the pressure drop can be calculated, and the strategies to transport cumin from the last unit operation to storage tank are assessed. Finally, this is critical for minimizing energy consumption, prevent cavitation, maintaining steady production flow, and ensuring safe plant operations.
Okay, so now I will explain the mass balance for the non-reactive unit operation, which is the depropanizer distillation column. So the purpose of the depropanizer is to separate the light hydrocarbons from the heavier components in the reactor effluent system. So the feed stream entering the column, denoted as F1, which is feed 1, has a total flow rate of 69.50 kmol per hour. The composition of this stream consists of 34.72% benzene, 19.42% of propylene, and 43.51% of cumin, and lastly 0.9% of the IPB, which is diisopropyl benzene. And lastly, we have 1.44% of propane. This is important to note that propane acts as an inert hydrocarbon impurity, which originates from the propylene feed stream entering the alkylation reactor. Since the propane does not participate in the chemical reaction, it leaves the reactor unchanged and enters the depropanizer together with other components. So because the depropanizer is a non-reactive separation unit, no chemical reaction occurs inside the column. Therefore, the overall mass balance equation can be written as F1 equals to P1 plus P2, where P1 represent as the overhead product, while P2 represent as the bottom product. So in this analysis, we would assume perfect separation for simplification. This means that all light hydrocarbons, which are propylene and propane, exit through overhead stream, while the heavier components like benzene, cumin, and the IPB leave through the bottom stream. Okay, so next I will explain the energy balance for non-reactive unit operation, which in this case is the depropanizer distillation column. So there are several assumptions were made to simplify the analysis. First, the reference state for components were defined as benzene in liquid phase at 25 degrees Celsius at 1 atmosphere, and propane and propylene in the gas phase at 25 degrees Celsius and 1 atmosphere pressure. For cumin in gas phase at 25 degrees Celsius at 1 atmosphere pressure, and the IPB is in liquid phase at the same reference condition. So the system is assumed to operate at steady state, meaning that there is no accumulation of energy within the unit over time. In addition, shaft work is assumed to be zero, since the distillation column does not contain any mechanical service such as turbines or compressor that perform work on the system. Heat loss to surroundings is also negligible, allowing us to assume that the heat transfer only occurs within the process of stream. Another simplifying assumption is that the feed stream enters the reactor at the same temperature as the reactor operating temperature, which eliminates the need to account for additional heating or cooling of the feed. For the energy balance calculation, only the main reaction heat is considered, which correspond to the formation of cumin from benzene and propylene. The formation of diisopropyl benzene or DIPB is neglected in the heat calculation because its selectivity is very small, approximately 2%, and therefore its effect on the total energy balance is so minimal. So the reactor is assumed to operate at 250 degrees Celsius and 25 atmospheres pressure, which are typical industrial conditions for the cumin alkylation process. So based on this assumption, the overall energy balance is simplified to the sum of the enthalpy of the inlet streams being equal to the sum of the enthalpy of the outlet streams, together with the heat generated or removed from the system. This approach allows us to determine the heat duty required for the process, which is important for us to designing the heating and cooling requirements of the plant.
Hello, in this section, I will explain the mass and energy balance of the alkylation reactor used in the cumin production process. So the reactor operates at 250 degrees Celsius and 25 atm, where benzene reacts with propylene to produce cumin as the main product. So several assumptions were made to simplify the analysis. So the reactor is assumed to operate at steady state, meaning there is no accumulation of mass in the system. Then the total feed entering the reactor is 101 kilomole per hour, consisting of benzene, propylene, and a small amount of propane impurity. Then the propylene conversion is assumed to be 70%, with 98% selectivity towards cumin, while the remaining 2% forms the IPB. Propane is treated as an inert impurity, so it does not participate in the reaction and leaves the reactor unchanged. So there's two reactions for cumin and mass balance. First is the main reaction, which is the alkylation of benzene with propylene to form cumin, and the side reaction where cumin reacts with propylene to form diisopropyl benzene, or the IPB, which is an undesired byproduct. So using these assumptions, a component mass balance was performed to determine the outlet composition of each component. Then, the mole fraction and mass fraction were then calculated using these formulas to better understand the composition of both the feed and product streams. So next, the molar flow rates were calculated and then be converted to mass flow rates using molecular weights. So this confirmed that the total mass entering the reactor equals the total mass leaving the reactor, satisfying the overall mass balance. So next, we'll be moving on for energy balance of reactive unit operation. So for energy balance, the reactor is also assumed to operate at steady state, with negligible kinetic and potential energy changes and no shock work occurring in the system. The energy balance relates the enthalpy of the inlet and outlet stream together with the heat of reaction. So we use this formula like here for general energy balance, and then the reference state is set the same as the non-reactive unit operation, which is 25 degrees Celsius and 1 atm. So the enthalpy values calculated earlier in non-reactive can be used consistently. So using these values, the heat reaction was determined using the heat of formation method and showing that the reaction is isothermic. So finally, the extent of reaction was calculated using propylene as the reference species, and the overall energy balance determines the heat duty of the reactor, which represents the heat that must be removed to maintain the reactor temperature. Thank you, guys.
Hi, so I'm Lim Ming Yang and I'm going to present about the piping layout. As you can see, this is our piping layout. For the pressure drop calculation, we are going to present for pipe P4 and pipe P5. Both transport the IPV. So for the P4 calculation, here is the piping layout. As you can see, we are using a 14-meter pipe. Here are the given information. By using this information, we can find the mass flow rate, volumetric flow rate, then finally the velocity. Find Reynolds number. We use this formula that we can determine the Reynolds number, which is 1108.8, which is a laminar flow. So for a laminar flow, we can use this formula. We can get the friction factor. Then after that, we plug it into the friction loss formula. For the friction loss formula, here are the formula. So there are 3 fittings, as you can see from here, 1, 2, and 3. So there's a sudden contraction here and a sudden expansion here. So that's why we need to plus 0.5 and 1, as well as the 0.46 for the fittings. So we can get the friction factor, friction loss of 0.023 joule per kilogram. After that, we apply the formula to the energy balance, and we can get the pressure drop, which is this one. Next, we will go to P5 calculation. P5 calculation is much simpler because there is no change in height. As you can see, it also transports the IPV only with a pipe length of 7 meters. So it's the same as P4 calculation. We find the velocity 0.04 because we are using the same pipe, so the diameter is still the same. So since to the friction factor, everything is still the same except for the friction loss. So as you can see, there are no fittings here, as well as there is a sudden expansion here. So we only plus 1 at here. So you can find the friction loss. Then by applying the formula, to the pressure, the energy balance, we can get this pressure drop.
Next, we are going to look at the strategy to deliver the main product, which is cumin. So first of all, after we separate cumin from the distillation column, it will pass through heat exchanger to reduce the temperature into 25 degrees Celsius. And then go through pump, which is a diaphragm pump with the efficiency of 85%. The reason we are going to use diaphragm pump, because diaphragm pump can handle most type of fluids. Then, the pipe length that we are going to use is 1 SK240 carbon steel pipe with a total length of 7 meters. Next, for the storage tanks, because of cumin is a flammable fluid, so we need to take some safety measures. So first of all, we are going to fill the nitrogen into the tank to avoid any fire and explosion, because nitrogen will decrease the oxygen content in the tank, so the risk of fire and explosion happen in the tank could reduce. Then the second safety measure is install static eliminator. Install static eliminator will eliminate any static electricity by neutralize the charge that exists in the tank. Next, let's look at to the specification of the storage tank. So for the materials, we are going to use stainless steel, because stainless steel is highly resistant towards any liquid, whether they are corrosive or not. Then for the shape is cylindrical with a height of 10 meter and the internal diameter is 4 meter. So the maximum capacity of the tank is 125.66 meter cube. Taking that the velocity of fluid is 1.66 meter per second, so the estimated daily production is 84 meter cube. So the maximum capacity need to be larger than daily productions, because we are going to prevent any risk of overflow. Let's look at how to calculate the work pump. So first of all, we are calculating the Reynolds number, which is 58381.55 with the friction fraction that have been calculated, which is 0.006342. So we get the friction loss is 9.330 kg. By using Bernoulli's equation, we get that work pump is equal to friction loss, because there is no pressure difference, there is no velocity difference, there is no elevations. So we get that that work pump is equal to the friction loss. So by using the formula of power, we got the work pump, which is 11.06 watt. Conclusion: this integrated design project have developed a deep understanding of concept towards those two courses, fluid mechanics and also PCE. Fluid mechanics requires a deep understanding of concept to design the pipe layout and determine the size and material of the pipe, while PCE is very important for us to know how to optimize the process and also the productions. That's all from us. Thank you.